Now that we hopefully all have at least basic understanding of monads and how to write monadic code, either by using explicit bind and return or by using do notation, we can look at a very important monad for Plutus, namely the contract monad. And maybe you have already seen that in the code examples I provided. So the contract monad defines code that will run in a wallet. So that defines the off-chain part of Plutus and is equally important to the on-chain part. But before we go into details with this contract monad, I also want to talk about a second monad, so-called emulator trace monad, because quite a few of you asked me whether we really need the playground to test Plutus contracts and whether there's a quicker, easier, and faster way that doesn't require you to start this playground server and then always manually copy paste over into the editor and so on. And there is indeed, and this is done via this emulator trace monad. And you can think of a trace in this monad, a program in this monad, as what we do manually in the simulator tab of the playground. So there we always define the initial conditions and then defined action. So we said wallet 1 does this, invokes this endpoint with these parameters, and then we wait so and so many slots, and then wallet 2 does this, and so on. And things like that you can also do in this trace monad. So we should look at that first. Emulator traces are defined in module plutus.trace.emulator in package plutus-contract. And we see that emulator trace A is a type abbreviation, type synonym for some very complicated looking effect monad. This is what I mentioned before, that the Plutus team used so-called effect system to build custom tailored monads, including this emulator trace monad. But we don't have to worry about that, what that means. So before we look at how to define traces, let's first look at how to run them. And the most general way is this run emulator trace. So it takes an emulator config, a phi config. We will look at those two in a minute, and a trace with unit result, and then produces a triple. And note there is no IO here. So that means this run emulator trace is a pure function. It's a pure function without any real world side effects. And this triple, so it's a list of emulator events, then maybe an emulator error. So if there's no error, that will be nothing. And if there is an error, it will be just the error, and some emulator state. Okay, so let's look at the configs. So we have the emulator config, which just has one field of type initial chain state. So let's look at initial chain state. And that is either an initial distribution or TX pool. So let's look at initial distribution. And that is just a map from wallet to value. So it just specifies key value pairs where the keys are the wallets and the value is the initial value. Value can be ADA, but it can also be native tokens. But we'll get to native tokens in a later lecture. There's a default distribution. We can look at that in the REPL. And there's also something called default distribution 4 if you want to specify how many wallets you want to have. The default distribution, I think, uses 10 wallets, and here you can have a list of those wallets you want. And then you get an initial distribution by specifying the wallets. So maybe we should look at that in the REPL. Let's start the REPL. It doesn't really matter, but we can load the trace module. And we need to import Plutus contract trace. Do we have this initial distribution? Yes, it's available. So we can look at the default distribution. Okay, and we see it has entries from wallet 1 to wallet 10, and each wallet gets, I believe, 100 ADA. This default distribution 4, as I said, takes a list of wallets. So if we, for example, only want wallet 1 and wallet 2, then we don't have wallets 3 to wallet 10, and just wallet 1 and 2, and they too have 100 million ADA. If we in the REPL import Plutus contract trace again, and then plutus.trace.emulator and data default, and ask for emulator config, then we see what we saw before in the documentation, but we also see that it is an instance of the default class that I explained in the last lecture. So if we look up the value of the default value for emulator config, we see that we get initial chain state left. Recall that was the initial distribution. And we see this is exactly the default distribution that we saw just now. So 10 wallets with 100 ADA each. Back in the documentation, so we now played a bit with initial distributions. Of course, if you don't want the default value of 100 million ADA, you can just give an explicit map where you specify exactly what values you want. Let's look at the other option. This was the left option. Let's look at the right option, this TX pool. And we see this is just a type synonym for a list of transactions. And as it says here in the documentation, in the comment, a pool of transactions which have yet to be validated. So instead of providing an initial distribution, you can also provide an initial list of transactions that will be applied. Okay, so now this was initial change state, which we needed for emulator config. And if we go back to this run emulator trace, so we have looked at the emulator config. So what's the fee config? And we see this is a record type with two fields, field config constant fee and field config scripts fee factor. So the constant fee per transaction in Loveless, so that's what you will always have to pay. And then a factor by which to multiply the size dependent scripts fee. So this is just some calibration factor. So the size depends on the memory consumption of the script and the runtime, the number of execution steps, and that then gets multiplied by this constant. If we go to the REPL again, load our module again, although that's not necessary, and import ledger.fee, and again data.default, and ask for fee config. Then we see what we just saw, and we see that this type is also an instance of default. So let's look at the default. So there's a flat rate fee of 10 Loveless. So the total fee will be 10 plus 1 times whatever the memory consumption and execution steps are. So let's load Plutus Trace Emulator again. So recall we were looking at the run emulator trace function. And now we have looked at emulator config and fee config. And we can use def for both. So we can use run emulator trace def. So the first def will be the default emulator config, which gives us 10 wallets with 100 ADA each. The second one will give us the default fee config. So now all that's missing is an actual emulator trace. And we haven't looked at how to construct an emulator trace yet. But we know, because I told you, that emulator trace is a monad. So without knowing anything else about emulator traces, we know that we have the standard monad operations, return and bind, available. So in particular, return. So the simple most emulator trace we can possibly write is the one that immediately returns unit. So it doesn't do anything. It doesn't call any contracts, doesn't wait for any slots. It immediately returns. So let's try what this gives us. And wow, we get a lot of output. And that's mostly due to this list of emulator events. So even for a contract, for a trace that doesn't do anything, we have many screens full of events, which also demonstrates that this is not very useful for trying out a contract in the REPL, because there's just too much information. But luckily, there's also something called run emulator trace IO that just takes an emulator trace, no configurations. So those will just be the default configurations. And it's not a pure function anymore. It just writes something to the screen. So we can try this with our trivial trace that immediately returns. And we see we get a much more concise output. So we see right in the beginning, a transaction is validated. That will be the Genesis transaction that distributes the initial funds of 100 ADA to the 10 wallets. And we see it waits for a slot or two, and we get the final balances. And because we haven't done anything, those final balances are still the initial balances of 100 ADA. Sometimes, of course, you do want to specify a different initial condition, or you want to have more fine-grained control. And for this, there's a variation of run emulator trace IO, which is called run emulator trace IO prime. And that does take an emulator config and a fee config, and in addition also a trace config. So what's a trace config? That's a record type with two fields. The second one is a handle, and in Haskell a handle can be a file, but it can also be the console. So the default would be that it's the console, but you can also specify a file. So what we saw right now in run emulator trace IO, there the handle is the standard output. And we have a field show event, which takes an emulator event prime and returns a maybe string. So here the idea is we get this list of all the emulator events when we run the run emulator trace function, the one with so much output. And then for each such event, we can specify either nothing, which means that event will be suppressed, or just the string that should be displayed for that event. And this trace config is also an instance of default, so we can use def for the default trace config, which will be the one that's used by run emulator trace IO, which shows very few events as we saw. Now let's look at the more interesting trace. And I copied the contract from the last lecture, the vesting contract, into the code for this week, and I'm importing it here. And last week we tried it out in the playground. Now let's do the same in a trace. I must mention, however, that since last week there has been a change in Plutus, so the vesting contract from last week won't compile anymore with the version of Plutus I'm using for this week's lecture. So there's a new type now called built-in data. And where before low-level Plutus used data to data to data to unit as the signature of a validator, so datum, redeemer, and context were all represented as data. Now they're represented as built-in data. And practically that means that we have to convert between data and built-in data at some points. So one point where this is relevant is we had this class isData, and recall that had the toData and fromData methods. So if type A is an instance of isData, then you can take an A and convert it to data, and you can take data and maybe convert it back to an A. So it's like serialization and deserialization. Now, if we want built-in data, there are two more functions that can do the same for built-in data. So take an A and convert it to built-in data, and deserialize a built-in data into maybe A. And there are also conversion functions from data to built-in data and back. So I had to modify the vesting contract to take this into account. And in this case, there were only two spots where I had to do something. So one was here in the off-chain code where I construct a redeemer, and before the redeemer took data, and now it takes built-in data. So instead of using Plutus TX to data, I'm now using Plutus TX to built-in data to convert unit into built-in data and then construct a redeemer. And the other position where I had to change something is here in this filter function. So once I get the datum before I deserialized or tried to deserialize it to D, which was this vesting datum type. And now I instead have to use from built-in data because now it's no longer data, now it's built-in data. So I had to make those changes to make the vesting contract compile with the up-to-date Plutus version. Now let's do the same in a trace. So I find a trace and I use do notation. So the first thing we have to do is what the playground does automatically, start the contract in all wallets that we are interested in. So we only need 2 wallets, so let's start it in wallet 1 and wallet 2. And for that we have a function in this emulator trace monad, activate contract wallet, and it takes a wallet, so wallet 1, and it takes the contract we want to activate, which was called endpoints. It's always called endpoints if you want to try it in the playground. Of course, we could choose another name if we are not worried with the playground. Now this monadic function in emulator trace actually returns a value. It returns a so-called handle that we can then use with other functions to refer to this specific instance of this endpoints contract. So we use do notation and this bind, so we bind the result, the handle, to h1. Now we do the same for wallet 2. And now we can actually call an endpoint, so we can call the endpoint give on wallet 1, and that we can do with call endpoint. We have to specify which endpoint, and this uses some advanced type level Haskell. So the syntax is add and now the name of the endpoint, give in our case. Now we have to specify the handle, so on which instance of the contract do we call this. We did that in the UI in the playground as well. I mean, we clicked on wallet 1 or wallet 2 depending on where we wanted to do this. So let's do it on wallet 1. And now we must specify the parameters, the values we give to this endpoint. So in the case of give, that was the give params data type, and that had 3 arguments: the beneficiary, the deadline, and the amount. The beneficiary should be wallet 2, and it must be wallet 2's pub key hash. And we can do that with pub key hash wallet pub key wallet 2. Now the deadline, let's say slot 20, and the amount, let's say 10 ADA. Okay, so this will call the endpoint. Now for wallet 2 to grab it, for that to be successful, the deadline has to be reached. And another thing we can do in the trace monad, apart from activating contracts and calling endpoints, is also waiting, either for a number of slots or until a specific slot, similar to what we did in the playground as well. So that is wait until slot. So we can say until slot 20. And this will actually return a value, namely the slot we have reached. So in this case 20, but we are not interested in that. And in order to avoid the warning, we can use void from data functor, which basically ignores the return value and turns it into a unit, and then we don't get the warning. Okay, now we want to call the grab endpoint on wallet 2. So that's grab. And the handle now is h2. And the parameters, the grab endpoint didn't take any interesting parameters. It was just unit. And finally, let's wait another slot to see the effect. And for that, we have wait n slots 1. In order to test that, let's define tests IOUnit, and let's just use this ren emulator trace IO with the trace we just defined. Now in the REPL, I can invoke test, and we see our trace. So we see this is the Genesis transaction, and we see that we started these two instances for wallet 1 and wallet 2. So this is very similar to the trace output you also see in the playground. So here we invoked our GIF endpoint, and the transaction was submitted and validated. Here we see a log that comes from the contract. So the log messages that we do inside the contract monad, inside the off-chain code, are actually well visible in this trace. Then now we reach slot 20, and the grab endpoint is called. Transaction is submitted, validated. We wait until slot 21, and we get the contract log message, collected gifts. We see that wallet 1 has 10 ADA and 10 Loveless less, so that's the 10 ADA gift and 10 Loveless transaction fees. And wallet 2 has roughly 10 ADA more, but had to pay more transaction fees because the grab endpoint involves validating a script, which is a bit more expensive. One other thing that we can do in the trace monad is logging. We saw that we do see the log messages from the contract monad inside the trace, but we can also explicitly log from inside the trace monad itself. So for example, if we want to log the slot we reached here at the end, instead of ignoring the result of wait and slot, we can bind it to a name. Let's call it S. And then we can use extras log info. That takes a string reached show S. In the REPL, if we reload and run the trace again, the result is almost completely identical. The only difference is this one line here, user log, and there we see our message, reach slot, get slot 21. So the next line as before is from the contract monad. Now let's look at the contract monad. The first thing you notice is that the type contract takes 4 type parameters.